Good afternoon, everybody. First of all, let me introduce myself. My name is Emiliano Pellis. I come from Italy, from the company GI Industrial Holding. I am the export area manager following the Greek market, together with other European countries. My Greek is limited to Kalimera, so considering the time and considering the topic, I'm switching to English, of course. The purpose of my presentation today is to show you an overview of the technologies and the refrigerant solution for the new generation of chillers in order to achieve high energy efficiency and low environmental impact when operating and supplying the air conditioning to a modern building. So the agenda for today is we start with some background information, the F-gas regulation, the Eco-Design Directive, and the green building practice. Then we move to the new chiller generation to explore the technical requirements, and we come to the conclusion. So let's start from the background. You know very well that the the European low carbon roadmap 2050 aims to prevent the global warming by, let's say, by dropping the total CO2 emissions by minus 80% in 2050. Of course, all the HVAC systems are subjected to this schedule, to this phase-down schedule for the total CO2 emissions. So the HVAC systems are supposed to contribute to such a schedule. Today, we focus talking about HVAC system, we focus in particular on the water-based system, so what we call the hydronic system, where we have the centralized production of chilled water or hot water, in case of chillers or heat pump. The water is then distributed to the piping system, to the terminal units, RME units and fan coil, in order to supply the air conditioning. So in particular, the chillers must contribute to the CO2 phase-down schedule through the compliance with some new requirements coming from the new legislation. And the new requirements are basically imposing the reduction of the TW for the chillers. TW is the total equivalent warming impact. You see in gray, the ground, the complete formula for the TW, and we can separate two contributions, what we call the TW direct and the TW indirect. The TW direct is related to the direct emissions of CO2, related basically to the direct release of refrigerant into the atmosphere. For example, in case of an accidental leakage or in case of refrigerant not recovered at the end of the life cycle of the machine. The TW indirect is related to the indirect emission of CO2, so linked basically with the energy consumption of the unit and therefore with the energy efficiency of the unit. If we look at the formula, it was working a few minutes ago. Okay. No. There is something. It's frozen.
Βγαίνεις ένα αριστάκι.
Θα κάνω, ναι. Δεν το πάζω για να ξεκινήσει. Και θέλει και χάρη ζεστάρος γιατί δεν ακούγεται από το λαμπίδι.
These figures. Magic. Seems to be okay. Okay, so let's try to restart. So total equivalent warming impact, direct and indirect. If we explore in details the formula for the TUI direct, we see that the TUI direct will depend mainly on three key factors. GWP, which is the global warming potential for the specific refrigerant compared to CO2, which has GWP conventionally equal to 1. Then there is M, which is the refrigerant charge, so basically the refrigerant content in kilograms for the chiller. And then L is the leakage rate. If we move to the TUI indirect, and again we explore the formula, we see that the TUI indirect will depend mainly on the factor E, which is the energy annual consumption. So basically depending on the seasonal efficiency of the unit. So we need to reduce the total TUI, the direct plus the indirect. We have now in the European market two new regulations playing towards this purpose. The F-gas regulation includes a lot of prescriptions, mainly playing on these three key factors, L, M, and GWP, so resulting in a reduction of the TUI direct. On the other side, the Eco-Design Directive is mainly related to the factor E, the energy efficiency, thus resulting in a reduction of the TUI indirect, thanks to the requirements, mandatory requirement coming from F-gas and Eco-Design. Further to this, there is a growing trend for the green building practice. And I will show you that if we go in details, what is, for a chillers, what is behind the contribution to, for a green building are again the 4 key factors, L, M, GWP, and D. So we have legislation introducing some mandatory requirements and then a good practice for the industry thanks to this trend for the green buildings. Everything playing to reduce the total TUI. Let's go ahead. Let's see very quickly some basic information about all the 3 pieces of the story. So let's start from the F-gas. F-gas, you know, is a very wide regulation. The main point of the F-gas is the phase down of the HFC, the hydrofluorocarbons, so the 14A or the 134A, for example. This phase down will result into a gradual reduction of the average GWP on the European market. You see the curve in red and you see the number in black. The number in black represents the average GWP expected in the market in the next coming years. But the process has already started. Further to this, the phase down of the HFCs will result into the migration from the traditional refrigerant, 14A or 134A, to new refrigerant with lower GWP, so lower impact on the environment. As a consequence of the F-gas, we know very well that the market price for the current refrigerant has grown a lot, more than 10 times in the last year. And we expect that in the future, the market price for refrigerant will be driven by the GWP. So the refrigerant with low GWP are expected to have a very stable market price in the next coming years, differently from the others, the traditional. Further to this, many countries in Europe have already introduced a local tax, an additional tax to the purchase price of each kilogram of refrigerant. This means that in some cases you can pay even the double price for a kilogram of gas. The price for the kilogram, the purchase price for each kilogram of gas, which is higher compared to the past, plus the local tax. Okay, so you can imagine. No? This is for the F-gas. Then let's move to the eco-design. Eco-design is the very wide directive again that sets the minimum efficiency requirement for the energy-related products, so including the HVAC system and in particular including the chillers. First of all, this is a very important news for the European market, differently from the US countries, because in the past, in Europe, every manufacturer could produce a unit with whatever efficiency and place it on the market. No issue. Now it's different. There is a minimum efficiency to comply with before placing a product on the market. And very important, the minimum efficiency is related not to the full load, but on the seasonal efficiency, as we know that the most part of most of the operating hours of the unit will be spent at part loads. Further to this, the regulation has introduced some new energy efficiency indicators, which are, for example, the SEER for chillers intended to operate in comfort cooling applications, the SEPR, which represents the seasonal energy efficiency for chillers intended for process cooling applications, and the SCOP, the seasonal COP for a heat pump, which is something new. In the past, we didn't have an energy efficiency indicator for the heat pump, a seasonal energy efficiency indicators. As you know, the jump in terms of efficiency on the market will be done according to multiple years, basically in a gradual way. Every 3 years there is a step above. So in such a way we increase the average efficiency on the market, giving the market the time to react, to the market and also to the industry, the time to react. So this is eco-design. The third point is the green buildings. You know, a building is green when its design, its construction and operation have been optimized in terms of impact on the environment. A building can be certified as green according to one of the existing rating tools. The most popular are the BREEAM from UK and the LEED, but there are also other rating tools, and basically the building needs to reach a score in order to be certified as a green building. There are many points that contribute to the achievement of this score. As you can imagine, one of the key points is the efficient use of energy within our building. And the HVAC represents, at least in the worst case, 35% or even 40% of the total energy consumption within a building. So you understand how important is the contribution coming from the HVAC system to become green. So in particular, if we explore in details, we realize that for chillers, let's say we get a good contribution, a good help, a good support to reach the green certification by working on these four indicators, M, L, GWP, and D. There are also other parameters, for example, related to the possibility to recycle the materials, but for sure these 4 factors are very important. So, taking into account this, what are in the end the requirements, the technical requirements for the new generation of chillers, both air-cooled, so intended for outdoor installation, or water-cooled, so intended for indoor installation, so in a technical room. The requirements are the future chiller will need to have the lowest content of refrigerant, the lowest GWP refrigerant, and a boost in terms of energy efficiency. So how to reach the lowest content of refrigerant? Through the introduction of proper technologies, like for example, a couple of examples, the microchannel coils in case of air-cooled chillers, or the hybrid film, and I will give you some more details very shortly on this. How to reduce the GWP of the refrigerant? Of course, moving to new refrigerant with lower GWP. For example, the new HFO family, hydrofluoroolefins. And again, I will tell you very shortly some additional information. Finally, we need the boost in efficiency. How can we increase the efficiency of a chiller? By introducing some technologies, the inverter technologies, by using the latest generation of heat exchangers available in the market, providing the top performance in heat exchange, and of course by implementing a smart control logic and a smart networking of our unit in case of a plant with multiple units. So these are the 3 points, and this is the summary of of the way that we need to follow to achieve the target. Let's see for the 3 points some more details. So, reduction of chiller refrigerant content. This is possible by using some technologies. I have reported here a couple of examples. The microchannel condenser coils instead of the standard copper aluminum coils. Through it is a system made of completely of aluminum, and basically through the system of parallel channels, we not only achieve an improvement in terms of efficiency thanks to the larger surface for the heat exchange, but we also reduce by 35–40% the refrigerant content of the unit. So this is very important, and this is normally an option on the chillers provided by all the manufacturers. Sorry, this comment is related to the part on the right. The hybrid film shell and tube evaporator. You know, in the market, there is the direct expansion evaporator, and there is also the flooded type, what we call the flooded type evaporator, which is the best one in terms of energy efficiency, because provide very, very low temperature approaches. But what is the negative point of the flooded type technology? That we need a lot of kilogram, a lot of gas. Indeed, we talk about flooded, okay? So the pipes are flooded by refrigerant. The hybrid film is a technology where, thanks to a special distribution system, we achieve very good performances similar to the flooded, but we limit the quantity of refrigerant that we need, resulting in a total reduction of 35–40% of the total refrigerant content. Basically, we make, thanks to the distribution system on the top, we have the pipe, and we try to have around the pipe only the minimum quantity of refrigerant that is needed for the process. To talk you very practically, the difference between the flooded and the hybrid film is like a relaxing bath and a fast shower. Okay, we need less water in the second case to reach the same effect, to clean ourselves. Second step, low global warming potential. Okay, this is a chart. The message behind this chart is this. On one side, we have the traditional refrigerant, 134A and 410A. We want to move to new refrigerant with low GWP, but at the same time, we want to have good availability, good price, and also, of course, similar performance to 410A and 134A, because we like the 410A and the 134A, but unfortunately, we are obliged to move to something new. If you see in details this chart, you see in particular this red line, which is the flammability line. What is above the red line is not flammable. What is below is flammable. The message is, if we want to move to a very good alternative solution with low GWP, we have to accept some compromise in terms of flammability. You know, 134A and 410A are A1 class, so not flammable, according to the ASHRAE classification. We have to accept this compromise. Why? Oh, sorry, excuse me. Why? Because most of the new possible alternatives belong to the A2L class. A2L class means midly flammable, okay? When we say flammable, of course, it creates concern in all of us, but there is also midly. Okay, what does it mean, midly? Midly means that we have to consider three factors. The concentration, the ignition energy and the burning velocity. When we talk about A2L class refrigerant, they are flammable only within a concentration range. Outside of this area, they are not flammable, exactly similar to A1 refrigerant. Second point, ignition energy. If we have the refrigerant, to ignite the refrigerant, we need some energy. And if you look at the graph here, you take the horizontal axis, here you have the ignition energy needed, the vertical axis. Here we have the ignition energy for the gasoline, which is something that all of us can easily identify as flammable. If we take one of the new refrigerant, for example this one, you see the ignition energy is definitely higher, is more than 250,000 times. Practically it means that the flame ignition is more difficult for A2L refrigerant. Last element, the burning velocity. The burning velocity for the A2L class refrigerant is very low, below 10 centimeters per second. This means that even in the unlucky case we have the flame will be likely to auto-extinguish. Okay, so all of this to say that A2L class are a good alternative to standard refrigerant. They are safe, and consider that the concept of A2L class refrigerant is now embedded in the standard EN378, which is the standard that all the manufacturers follow for the design of the unit. Okay? But now the point is, what are the viable solutions for the industry? It depends on the compressor technologies that we are referring to. So if we consider, let's start from here, that is easier for me to explain, the screw and the turbocore technology, so the centrifugal technology. Today the dominant solution, the traditional solution is 1348, GWP around 1300, A1 class, not flammable, group 2 according to the PED, not the Pressure Equipment Directive. What about the new possible alternative? They are the same for the turbo and for the screw, so let's look here. We have two, for example, these two good options are for 513A, which is a medium GWP refrigerant, around 600, so lower than this. A1 class, so again not flammable, and again group 2 of the PED directive. This is a good refrigerant because it is not flammable, so can be handled exactly as the 134A, and also there is a medium GWP, so a reduction in GWP, and there is also a very limited impact in terms of performance, in terms of cooling capacity and efficiency for the chillers. What is the other solution? The 1234ZE. This is one of the refrigerants belonging to the new family of the HFO, hydrofluoroolefins. Very low GWP, less than 1 according to the ISO classification of refrigerants. But this is A2L, so mildly flammable, and still group 2 of the refrigerant. 513A is a blend of HFO and HFCs. This new refrigerant, of course, is fantastic, is the long-term solution in terms of the GWP, but on the other side, this refrigerant provides a lower euro kilowatt. I mean, the unit, if we take a unit with 1348 and we fill the unit with the ZE, instead of 1000 kilowatt, the unit will give us 700, 750 kilowatt. Okay, so we lose 20-25% in terms of cooling capacity, even if the efficiency is slightly better than 1348. So it means that from our side, from the side of all the chiller manufacturers, we have to completely redesign the unit in order to compensate the reduction, the natural reduction in cooling capacity through an appropriate selection of compressor, of coils, of heat exchangers, of all the details. On the other side, the 5138 represents almost a drop-in solution. We just, let's say, it's not easy like that, but it's very similar. We have just to refill the unit. What we need is only to verify some points related, for example, to the material compatibility, so the oil, the gasket of the compressor, and so on, this stuff. What about the scroll? Here the situation is more critical for the market. Today the dominant solution is 410A. GWP around 2000, A1 class, group 2 for the PED. What about the new solution? All the market is waiting news from one of the gas producers because there is the R466A under R&D stage. Theoretically, this should be refrigerant not flammable and providing very similar performance to Fortenay with medium GWP. But it is something still at R&D stage, so we don't have reliable information yet about this refrigerant. So, waiting for the magic solution, unfortunately for the moment, the two realistic solutions that we can consider are both midly flammable. And one is R32, that is nowadays popular from the split, and R452B. Both the solutions are midly flammable, both of the solutions provide a medium GWP, around 700, and both of them are group 1 for the PED. What is the difference? This one, let's say, based on the pH diagram, let's say this one is suitable to heating and cooling application. The R32 is suitable to cooling only application. But with the 452B, we get very similar performance to Fortenay. With R32, we get better performance than Fortenay. And the euro kilowatt of the unit will be higher, meaning that our unit will be more compact and cheaper. Okay. So this is a picture giving you an overview of the possible, the most popular options coming from the industry for the refrigerants. And more or less, I can tell you that for the screw and turbo core, the solution is basically this is the most common solution. For the scroll, let's say, unfortunately, we don't have the crystal ball to see, let's say, in the long term what will happen. The third point is the high energy efficiency. I have tried to identify four key points to achieve high energy efficiency on our chiller. The first is the inverter technology, the introduction of inverter technology applied not only on the compressor, but also on the pumps, on the water pumps, on the fans. And second point is the use of the latest generation of heat exchanger, for example, with by using high-performing tubes and enhanced tubes, copper tubes, in the heat exchanger, the shell and tube type, for example. Third point, remote and proactive monitoring. So we need to via remote the chillers and introduce some corrective action in case of deviation. Yep.
Can I interrupt for a minute?
Yeah.
Are you taking long to finish?
2 minutes.
When you finish, you come
right.
for the open discussion. We have a drawing in the open discussion just to know your timetable. Thank you. We'll wait for you.
No more than 5 minutes.
Okay.
Thank you.
Thank you.
So, remote and proactive monitoring, and finally, a smart control of chiller networking in case of plant with multiple units. So we need, for example, to introduce a proper chiller sequencing in order to optimize the number of the operating hours, in order to have a good distribution, and to optimize the working point of the unit based on the peak of efficiency. To give an example, very practical, not typically a screw compressor has the peak of efficiency around 75–80% of its full load. So it is good that we take this into account when implementing the logic on the plant management. So all of this to achieve high energy efficiency. So as you see, there are many new requirements to comply with on a chiller, but I think that this challenge will provide a fantastic opportunity to the green building of the future. Thank you for the attention. Yes?
You said that you presented us a few charts about the light refractory liquids.
Yep.
How far is the danger zone from the normal operating conditions of a compressor using these liquids?
I can tell you that the Danfoss Turbocor was the first company in the industry making the test on the flammability, no? And you know the green Turbocor compressor is fitted with the ZE refrigerant, 1, 2, 3, 4 ZE. So they published the result of their test to show that the flame ignition is very. I don't have the slide to show you this. I don't have the slide with me, but they show how difficult it is to have the ignition of the refrigerant, and even in the unlucky case you have the flame, you will see the flame move and auto-extinguish. Okay, this is on one side. In any case, in the standard EN378, you will find some dedicated prescriptions. For example, if you have water-cooled chillers, so intended to be in a technical room, you will have to install additional ventilation in the electrical panel of the unit, and you will have to install, for example, the leak detectors, no? So there are, the refrigerant in the end is flammable, but mildly flammable, but let's say the risk level is low, but in any case the norm will tell you some additional cares that must be implemented in the room.
Sure.
Okay, that's it. What I can tell you practically is that this is valid in general. What is happening in Europe, and is different country by country, there is a problem in the building codes. For example, in Italy we have different regulation for the hospitals, for the school. So what is not clear today, but this is a problem for everybody, is the dedicated application, let's say, for each kind of building, okay? Because an office building, a school is different from an hospital, and so on. From our point of view as a manufacturer, let's say there is the norm now including the let's say the concept of the A12 class. So we know what are the prescriptions required on the unit, okay? And I can tell you that in some countries in the north part of Europe, so the Scandinavian countries, or for example also UK, they are using for example the leak detectors even on the air-cooled chillers, that are installed outside. But in any case, you can put the leak detectors. You have a first alarm, a beep, at first level, and then if the level of refrigerant is increased, you have a signal that can be sent to the BMS in order to stop the unit, for example.
Yes.
Okay, this is.
And maybe start fans.
So yes, exactly. So regarding the building code, I don't have the answer because it is still something ongoing. Regarding the unit design, yes, we know what must be done.
No, I was more concerned on.
Yeah.
I was more concerned on whether the operating conditions and possible accidents during the compressor working, and what is the distance from the danger zone of these?
There is I don't know the number, but if you take the standard, there is the indication of this distance. Okay. Yes, for sure. I remember clearly the picture showing the room, the machine, and the operator. So, and there is the distance. Well, I don't know. I don't remember the number.
Okay. Thank you for the presentation. And first question is if I can send you an email and take this presentation. That it's very good.
I think they are fine. Yes, right.
Okay. And the second question is regarding the second page of the presentation. You said that. HVAC, yes, the one, no, not the second, about fifth. Another one. Okay, that one, yes. HVAC represents between 40 to 50% of the energy consumption in a building.
Yes, this is.
In which estimation or assumption is this based? Because
yes,
from country to country, income to income, and many other.
Okay, no, it is different country by country and building by building. School, hospital, okay, it's different. For example, from the World Green Building Council, I took this chart that you see. This is related to a commercial building, and you see the HVAC represent 50%. If you take another kind of building, can be different, but normally it is very difficult that it is less than 30%. You can look at.
For example, in Greece, by Kenak, they say that it's 8%. 8%, yes. In Arabic countries, it's above 70%. In India, Delhi, it's 60-70%. In North Europe, it's about 8%, and so on, I think.
No,
Not I think
8%,
it's 2012 numbers of 2012 research.
yes, we are not giving, of course, exact numbers, but in terms of rough numbers, 8% doesn't sound
Yes,
good.
mostly Greek because we are stupid and we take the British regulation and bring and just translate to Greek, and we think this is correct. And after 10-20 years, maybe someone of the chamber think that they might convert it to the reality. That's the reason, I think.
I don't know. I ask
8% it's a very low number.
This low percentage.
No.
I'm asking to our not to our Greek partners here because I don't know the answer.
An estimation about Greece is about 30 to 35% during the hot season, and a
my
little less.
30-35 is a minimum, a reliable minimum.
Estimation about Greece, but Kenak has a different opinion. Kenak is the regulation of Greece regarding buildings.
To be honest, when preparing the presentation, I made a tour around the internet, and normally I didn't found a number below 30% when giving an indication about the part of HVAC. So I trust you, of course, but I don't know, 8% seems to be very low.
Okay.
Thank you.
Okay, thank you.